Good morning, doctor.
Yeah, how are you?
Yeah, fine.
You doing okay so far?
Yeah,
Is this course too hard or too easy?
it's it's not just the week 3 quiz. It's like just a little bit
Week
hard.
three assignment a little bit harder, right?
I'm the person. Yeah, I'm the
Okay,
person I ping you about the chance.
okay. I'll talk about that week three homework. Okay.
Okay, thanks.
Let me bring up the slides. Okay. Regarding week three assignment, a quiz, okay? It actually very straightforward and easy. Actually, we discussed it in week two or week one, okay? When we discussed the rotational metric and displacement vector. So here I'm going to redo it again, try to give you the idea of how we set up the metric for the displacement vectors. Okay, so I'll go over that again. Let me bring up the related slices. Okay, it's on this one, rotational and metric and displacement. Okay, so first that let's go back to the fundamental things. Okay, so we do have a coordinate x, y, okay, x and y. So here we may have some point that's actually say, let's just say it's a 1, 1, okay. So if this point move from 1, 1 to 2, 2, okay, you have a vector of going 1, 1 this way to go there, right? So this one is this x naught, y naught, okay, this is x1, y1, okay, so you are x1 should be your s naught plus 1. Your y1 should be y naught plus 1. Okay, so your x1, y1 vector is x naught, y naught vector plus a 1, 1 vector. This we call it displacement vector. Okay, it's how much you travel from the original point to a destination point. Is that okay so far?
Yeah,
No question?
no question.
Okay, no question, that's fine. Let's look at the other way to look at this. This is things, okay? So let's assume that your xy is right here. Okay. This time, your coordinate move. Let's assume you move to here. So you have big X and big Y system here, okay? So originally you have a point that actually is 2, 2 here. So this is small x, small y is 2, 2. If you use a large X, large Y to measure it, it should be 1, 1, right? So this one here is actually 1, 1. Its coordinate move here to 1, 1, okay? So the relationship of the x, big X, big Y is X will be equals to big X plus 1, okay? Y will be big Y plus 1, okay? So basically your big X actually big Y vector should be moved to here. This one, and I'm sorry, this one moved to here, okay? So it should be the small x, small y minus 1, 1, or small x, small y plus minus 1, minus 1. Okay, so these two observation frame, your original frame and this frame, that create a displacement vector. It's similar like your object move this way. Okay, similar to like that. Okay, a little bit similar like that. So basically, what I'm trying to say right here is that your object movement this way is equivalent to your frame movement this way. Okay, the two things is actually the same. Okay, it's the same. So you create displacement vector, but usually when we calculate, we don't depend on this displacement vector. Okay, we don't depend on that displacement vector. Let's look at the so-called okay, let me point out one more thing. Okay, so there's a rotational matrix and there is a displacement vector. So let's look at another one. Should be this one. Okay, let me see. This one here. Okay, this one actually, this page we spend some time on it. So let me explain this page one more time. So on our system, okay, there are many transformations. Okay, so linear algebra is used for transformation. Okay, you multiply a matrix, it causes transformation. Okay, so the transformation we talk about in geometry that including not only these. Okay, they are more than this. They are okay. Let's look at it. Search linear algebra for transformation matrix. Okay, so there are several things that actually linear algebra can be used for transformation. Okay, but what kind of transformation? The transformation including enlarge and making things smaller. That's called scaling. Okay, also including rotation, also including translation. Okay, these are typical transformation we will see in the system. Let me bring up one more slide. Okay. So there are several motion we may have, and then let's see. Rotational metric. Let me see this one. Now this one. Okay, let me bring up another one. There are many let's see, okay, one moment, because we have too many slices, and this had already been several weeks ago. Okay. Cannot find the slices that I want. Okay, so basically, let me see whether this one has all of the translation. So there's one that we have talking about every other translation. I'm sorry, I keep up. Okay, I keep up, and they may not be fully directly related. So anyway, you will have a scale, you have a rotation, you may have translate, you also may have skew. Okay, You may also have mirror. Okay. There are many other things that would related to the transformation. Let me bring up an interesting page. Okay. I think of something that may help you. So last night I just teach some kids for website design. Okay, not this one. Last night I just teach some kids for website design, and web pages they have picture, and then you can work on the picture for the translations. Okay. So it should be this one. Okay, let's look at this one. So basically, what kind of transformation that your image or your object may go through? It's actually like this. Okay, they are CSS translation. So you have the skew. Your image may undergo skew, and each of the skew, you may use the linear algebra metric to do transformation. You may scale down from big one to small one. Same thing, one metric can do it. Okay. You may do this scale X, scale Y, okay, and do rotation as well. Okay, this is rotation. So image graphics and also the coordinate changes and robotic motion is the same. They all be able to be solved by linear algebra. Okay, they all can be solved by linear algebra. This is a simple thing like that. And then they are width size. Okay, they are width size. Let me show you the width size. There are websites that you can work on the transformation that you want, scale, rotate, skew, and translate, and you generate the CSS code that you can plug into your page. Okay, and there are also 3D things, 3D translation as well. Okay, so let's look at this 3D visual site. Okay, these are some website, and you can do 3D shear, scale, right? Make it longer or smaller. These are scaling, and also rotation. Translate. Translate means movement. So when we say displacement, that is the movement. So the object movement is the opposite of the frame motion. Okay. So basically, you can play around these different things. And then what happens is right here, there is a 3D rotational metric is right here, transform metric. 3D transform metric is given right here. You can see the parameter, 3D metric, okay? For the transformation is right there. Okay, so there are tools you can visualize your scale and whatever, right? And here we are talking about when we apply to robotics. Okay, the metric tool I posted in the chat. Okay, and then okay, it's just to show you that okay, there are a lot of things that we can solve by math in order to get the effect. So now let's look at the homogeneous transform metric one more time. So originally you have S1, SY only. Okay, you have two-dimensional vector, right? But we want to convert it to the homogeneous transform. So we put a one, add one more since one over there. Okay, add one over there. This one is just for the purpose of homogeneous transform. Okay, and now number one. Number one is that if you have the scaling, your new SY can be expressed by scaling factor of the original SY. So basically your SY prime will be equal to a SX S1 scaling factor top. This is a vector inner product of vectors. Okay. If this is vector times vector, but this vector times vector, you can put it down as SX0 XY times XY. Then the same multiplication can be expressed by matrix. Is okay? If we are to scaling. So it doesn't hurt that actually if you put a 1 over there, if you put a 1 over there, let's look at it. Okay, so here what happened is only for this scaling only, okay? For this scaling only, you do have Sx0, Sy. Okay, this original metric. Okay, I'm sorry. This is original metric. That's actually expanded. Okay, expanded to be the newer metric. Okay, so the new metric is Sx0, 0, Sx 0, 0, and here you have 0, 0, 1. Okay, this extra line here is only for displacement only. Okay, times sy1. You create a new vector called syw. Okay, s prime, y prime, w. So this one, you have sx0 times sy1. So you get sx, x. This one multiply this one. You get s, this is 1, okay, sy times 1. This one times this one, you get 1. Okay, so this one actually is sx times x, sy times y, and 1. So basically, you expand the vector multiplication to metric format, okay, without problem. So that's the scaling vector. Same thing for the rotation and displacement, the same. Okay, let's look at the last one, translation. So translation, we do have the effect of the, we do have the final result that we want to have is sy, big S, big Y should be equal to x1 small x plus this displacement vector as we shown a moment ago, right? So you put a 1 there, it doesn't hurt, right? If you put a 1 there, it doesn't hurt. Now let's actually further put into the equation. So let's use the right hand side. 1, 0, 1, this is things, okay? So right hand side you have 1, 0, 0, 1, 0, 1, AB1. This AB is your displacement vector, okay, times SY1. What happened is this one multiply this one. You got X plus A equals X point. Right, this is X point. This X point will be equal this times this. Same thing, Y prime will be equals Y plus E. And the last one, 1 equals 1. Okay, so basically this one is you also convert your translation equation into a metric format like this. So overall, your scaling can be converted to metric format. Your rotation can be converted to metric format. Your translate can be converted into one metric format. And we don't have the scaling in robotics so far because we are talking about rigid body. So your robot is not supposed to be grow or shrinking. Okay, so basically, then you do have this rotation and translation, and you combine them together. That become your HTM, homogeneous transform metric. Okay, they do have this dilation, rotation, reflection, here, translation, different kind of transformation. Okay, we list down here, but we only have the rotation and translation. Okay, and they can be done by the matrix. So in the chapter 3 quiz, we only cover up to here, nothing even harder. Okay, if you watch the video, it should be fine. You should be able to solve the problem. Any questions so far? For quiz 3A. Any other
No,
question?
doctor. Yeah,
No other
no.
question? Okay.
No. It's
okay?
fine.
But it's okay to ask, okay? And usually you send email to me slower, okay? I say that I'm not full-time professor, so I may check the email 2 days, 3 days later, okay? So it's better you just send me a Facebook message, okay?
Yeah,
And
definitely.
I'm all the time there, okay? I'm all the time there because I'm teaching the account I give you actually is my educational account. Okay, so you do type HTTP, okay, and then Facebook.com, okay, that's Dr. and okay, Eric Chow. Okay, it's very easy to remember, okay. And you need you to hear a friend to me, okay, and every day I deal with all kind of student, AP, banana team, okay, it's a Kiwi team for website design, C double plus students, user for competition student, usually it's everyone right here, okay, and one more all girl coding club, okay, and parents and whatever, a lot of people. So I need a lot of students compete in USACO or C double plus events, okay? So you post it here, I kind of talk to him. Like this one, there's one student, this female student at the UCLA. He was my former high school student, and he told me I'm stuck or whatever. Okay. He told me I'm stuck. And then I told him I will find a time to answer your problem and send him some of the slices I'm using for class book to her. Okay. So that's a better way to communicate because you wait until your email arrives and the communication is not real time. And also, I may misunderstood your intention. Okay. And email is a very bad way of communication. Okay. So I prefer you just post message to here. And I usually check it every day, every time, but I think worst time response time would be within a day. Okay, within a day, should be able to talk about it. So this is student particularly asking me about how to write a tokenizer. Okay, so I'm sending the tokenizer information to her. Okay. Okay, so that's a better way to communicate with me. Okay, remember my website, my Facebook is facebook.com/dr as Dr. Okay, Dr. Eric Chow. Okay, that would be a better way to reach me. I would actually respond faster there. Okay.
Yeah, okay, doctor. Thank you so much.
Any other question?
No.
As for the quiz, I usually don't give away the answer. Okay. Why we are doing that? Because there are students still haven't submitted the quiz yet. Okay. So I cannot give away the answer. That doesn't make sense, right? Someone still haven't taken. And also I committed to the exception of the late submission, right? If we take away that, we can send answer to student, but since they are still students taking the exam, so we cannot send the answer right now. Okay. So, but to make up this, okay, it's really ugly. Okay, there are still 2 students haven't taken any of the tests yet. But if the whole class, okay, I may grant one more attempt. Okay, that's what we can do right now. So this one is better. Okay, more green. Okay, more green. So I watch it. Yeah, every year the 3A is more terrible because some students are not prepared for the math. The first two quiz are too easy. Okay, and then the problem get harder. So this one we consider to give one more attempt. But too bad these 2 gentlemen didn't cooperate. Okay, they should submit earlier. I cannot send out the invitation for another attempt before they actually even work on the first time. Okay, that's the problem. Okay, and I will try to grade the programming homework today or tomorrow. Okay, that's the grading part. Everyone so far doing great, I should say. Okay, quiz are harder, yes, but that's the part that we actually can be to can differentiate students' work. Okay, usually the programming assignment, if you are not too far, you are not totally giving me garbage, I will give you a good grade on programming assignment. Okay, but the quiz part, you have to study. It's auto grade, so we don't make up the score. Okay, we don't make up the score, so you have to really study. Okay. Any other question? Okay, no question. Let's look at today's this week's. I will just give summary. Okay, the main topics, the main ideas. You still need to study the video, and because we cannot finish 2 hours, 3 hour talk right here. Okay, and we do actually have two lectures, and in combination, there are more than 4 hours of the lecture, so we cannot do it real time every year. Okay, so right now I make this a class meeting primarily for the discussion of your questions. Okay, and help students who cannot solve some problem. Okay, that's the main purpose of this class meeting. And other than that, I will give the idea of what we are doing this week. Okay, so for this week we are on lecture 10 and 11. It's on sensors and actuators. Okay. So sensor and actuator. Okay, let's go back to this robot conceptual diagram. So we work on a lot of the manipulator, how finger move, how wrist move, okay, and trajectory planner, like that actually do planning before sending out a control variable, okay, theta1, theta2. So that's actually this portion. Now we are going to look at the overall architecture. We still have a sensor we need to take care of, that sense the environment, okay, and send out information to controller, okay. And they are also control the computer to control the whole robot operation. So usually this is a microcontroller, okay. For example, Raspberry Pi, right? Raspberry Pi is a controller. But today our main topic is on the sensing and this week's main topic is sensing and actuators. Okay, so sensing is a total different story compared to the manipulator. And sensing's the main purpose is like this. Okay, sensing's the main purpose is you do have a robot. Okay, you do have a robot, but you want to work. Okay, so your robot has two major elements. One is robot's motion quotient. Okay, so let's assume that your robot is like a tank. So using the tractors. Okay. Now this one you do have a robot arm here. Okay. Okay, whatever robot arm. So you may have a sensor right here. So now let's look at the sensor's responsibility. This guy. So this guy has what responsibility? Anybody can answer it without referring to textbook, using your common knowledge. So what this sensor can do? Anybody know? Nobody know. Number one, you would need to do measurement. So major, there's some tree, how far away? Okay, there's some stone here. How far it is, okay? So after measurement, you build something called environmental model. So this robot arm, knowing that he is living in certain kind of environment. So there's a 3D model. Okay, there's a stone, there's a tree, will be stored in its memory. Okay, so first thing is the environmental model. You sense this, that you try to build up the environment model. Okay, and usually it's by measurement. Second, beyond measurement, second part is computer vision. So, for example, this robot arm is required to pick up black stone instead of white stone. So the computer vision must be able to tell the color. Is that okay? Hello? Any question? Any questions so far? No? No response. So basically, this computer vision must be able to measure the color of the stone so that he can pick up the right color of the stone or remove the right color of the stone. That's computer vision. But sometimes it's not this easy. Okay, it's not just the color. You actually may have the some sort of pattern. So right here, you also need to perform pattern recognition. Okay, computer vision, and maybe need to perform pattern recognition, and then make decision because how far it is. Okay, let's assume this time it's the real tank, not the contractor. Okay, so the real tank. Okay, so real tank. Okay, let's assume this is a real American tank. There might be some sensor. Okay, sensor. So there's another tank under here. Okay. So basically, based on the historical data, he needs this red computer, a red tank may want to know this is T80, Russian T80 or Russian T74, right? Or this one is the M1. If it's the M1, you don't shoot, right? If it's actually T80, you may just fire, okay, and shoot it, right? So there's a pattern recognition. And this pattern recognition will depend on what? Depend on the modern control of using the machine learning, okay, of the learning using the machine learning. So the memory is related to data science and AI, okay. Machine learning is related to data science and AI. And modern days, sensor need to have such a capability. Collecting the raw data, that should be the image of the tank, okay. And then based on the image of the tank, you need to use the machine learning to figure out whether this one is an American M1 or a Russian T72, 72, okay? Is that okay so far? So that's how this chapter is focused on. It's the computer vision part, okay? It's a computer vision. So computer vision, we have machine learning, we may get involved to learn and see. Three major problems you may need to solve, okay? Number one, regression. Okay, regression usually used when you actually trying to restore a black and white image to a full color picture. Okay. And second is the classification. Okay. You try to classify this object, and what we see here is actually a dog with a head. Okay. So this is a so-called classification. And then the other one is reinforcement learning. Okay. So let the prey break out. And then last one is the clustering. Clustering, you want to predict the prediction of the k-mean value for clustering. Okay. To figure out whether somewhere the crime rate is higher. Okay. I think this map is related to some India city. Okay. So they do have such a report there for helping to figure out. So machine learning as a whole is to help you to use the past data to understand the current physical events. Okay. Okay, so that's the machine vision, and this chapter mainly talk about the sensor and how they process the data. So there's a compute in our website. We have a lab talking about how the computer vision has been done. Okay. So when you build a robot, you need to build an end-to-end model. End-to-end model means that from the transmitting end of the signal or image to the receiving end of the image. Okay. Right here, this end-to-end model is a signal. It's an audio signal. Okay. And it got translated to the other side. So this is so-called end-to-end model. So in your robot control, you must set up a end-to-end model to get information from sensor until you give command to the robot arm. This so-called end-to-end robot model. Is okay so far? No? Any question? Hello, any question?
No, doctor.
Okay, no question, that's fine. So basically, this one is beyond only working on the robot arm, and we look at the so-called full end-to-end model. Okay, so this chapter like that. Okay, and then there's a double use system transfer system model. Okay, functions, and put it into the last transform domain. Okay, so this portion just for you to understand that people calculated it. Okay, you really do not need to set up this too hard. Okay. Other than that, actually, I don't see other things that and they are traditional resistor, capacitor, and inductors loop design. Okay, so loop design is that you finish the loop parameter estimation, and you start to use the so-called resistance, capacitance, and inductors network to finish the design. Okay, so this is just saying that. Okay, and final system diagrams like this. Okay. Any questions so far? Okay. If no question, I think that's about it for today. Okay. Okay. Again, if you want to reach me, try to use this Facebook Messenger that you get to meet earlier. Okay. Okay. If no question, that's it for today. Okay. See you next time. But remember, if you do have question, ask early. Okay. And on the Facebook, I will respond you faster. Okay. And email sometimes take longer time and then may create misunderstanding. Okay. Okay. See you next time. Okay.